This episode is sponsored by Brilliant. Approximately 2 billion years ago, the Earth was forever changed. A few 100 million years prior, a set of microbes had evolved a new ability, photosynthesis, turning sunlight into food and releasing oxygen as a waste product. At first, this oxygen was simply absorbed by the land and the oceans, but now it was spilling out into the air, changing the chemical constituency of the entire planetary atmosphere. The Great Oxidation Event had begun. Still today, after 2 billion years, photosynthesis persists as an undeniable evolutionary advantage, continuing to fill our atmosphere with oxygen. In the history of our planet, no other event so clearly advertises the presence of life on Earth, a cosmic signpost of Earth's biology to distant aliens. But could we be crossing a second such event, a transition from biology to technology, from instinct to sentience, the Great Awakening Event? Join us today as we explore the balance of biology and technology and the possibility of persistent intelligence. Our search for life in the universe is not really a search for life itself, but rather the marks, the scars that life imprints upon the cosmos. On the Earth, that's not how it works. If a biologist discovers a new species of insect, for example, it would almost certainly involve a physical sample of the insect. We could hold it in our hands, we could dissect it, experiment upon it. Perhaps one day we might be able to do the same on Mars or Venus, but when it comes to our search for life beyond the solar system, we are frustrated by the limits of our technology. The vastness of space changes the role of the scientist from an active, participatory experimenter to a strictly passive observer. For now, we are essentially trapped within a cosmic prison cell, able to peer out between the bars, but unable to touch the fruits that lie beyond. Yet more, our prison cell is effectively isolated on an island within a vast ocean. The next island is so far away that we cannot make out its shape or form, just a blurry, hazy point of light on the distant horizon. For now then, our quest for life in the universe involves squinting at these distant specks in the hope of seeing something about them which might betray the presence of life, the way that life might affect that speck of light. Broadly, astronomers approach this in two ways. There are biosignatures and technosignatures. Now, biosignatures refers to the natural biological activity happening on a planet that leads to detectable effects in our observations. So, for example, on the Earth, a classic biosignature is oxygen because of two reasons. First, it's being constantly produced by biology, specifically via photosynthesis in plants, microbes, and especially plankton. And second, oxygen is a reactive molecule that really shouldn't persist in an atmosphere unless something is making it. In a recent study, it was estimated that about 42 gigatons of oxygen is consumed every year from our atmosphere due to respiration, absorption, fires, and oxidation. If all life went extinct, then the Earth would run out of oxygen within something like 10,000 years or so. Astronomers like myself can also look for life via technosignatures, which, as the name suggests, refers to the technological activities of an advanced civilization. So this could be anything from a radio emission, such as a directed hello message sent our way between the stars, to anthropogenic climate change, the unnatural climate forcing happening on our planet right now. You can see then that technosignatures don't always have to be intentional signals. Even our space satellites could betray our presence to another civilization. But technosignatures are different from biosignatures in that they require a very special type of life, intelligent life that uses technology. A fun topic to spark a lively debate in any astronomy department is, what are we more likely to detect first, biosignatures or technosignatures? Now, in my experience, these debates tend to lean heavily towards biosignatures for reasons that we'll get into, but first I want to highlight that this is more than just astronomy small talk. It actually dictates the very design of upcoming NASA flagship space missions. Right now, NASA is in the process of choosing the successor to the James Webb Space Telescope, which itself is the successor to the Hubble Space Telescope and will be hopefully launching later this year. Two of the options under review are geared towards the search for life, HabEx and LUVOIR. Both of these are multi-billion-dollar missions that aim to ultimately seek biosignatures on nearby Earth-like planets, biosignatures. In contrast, there are no plans or even proposals for a multi-billion-dollar technosignature space mission. In other words, NASA and others are not even considering going the technosignature route. So this seemingly implies that the debate is settled, right? Biosignatures are always the best way to look for life. So, as many of our regular viewers know, I often like to think about the counter-argument, the less popular opinion. It's a great way to sharpen our thinking on this, to make sure that we're betting on the right horse, but it also reveals some interesting new insights. But before we do that, I want to thank the sponsor of today's video. That's Brilliant. You know, what makes us intelligent is our ability to learn and to adapt. Our minds are muscles that we have to continuously train. Brilliant is a gateway to do just that, offering over 60 rich courses in math, science, and quantitative finance. I encourage all of you to never stop learning, to become the best version of yourself. And this is a great way to do just that in a fun, interactive environment. There's even an astrophysics course including sections on cosmology and our favorite, exoplanets. You can subscribe and help Cool Worlds out by using the link brilliant.org/coolworlds, and the first 200 of you to use that link will get 20% off the annual premium subscription. What exactly is the case for biosignatures? Why did NASA and others conclude that this is by far the most promising path? There are many different facets to this debate that we could explore, but to keep things simple, I'm going to focus on what I would say are the three most important points: frequency, ambiguity, and persistence. The frequency argument highlights that intelligent life is, by definition, a specific subtype of life. What this means is that if 50%, say, of planets go on to spawn simple life, then the number of those that go on to spawn intelligent life must be necessarily smaller, and so intelligent life would be less common, although not necessarily by a lot. This seems like a clear win for biosignatures, but it ignores the possibility that intelligent life need not necessarily spawn on a planet for it to be present there. It could, after all, fly there from somewhere else. Certainly, life may also do this via the hypothesized mechanism of panspermia, that's life hitching rides on asteroids. But a civilization bent on galactic colonization is an inherently souped-up version of this. For now though, let's be generous and give biosignatures this point. Next up, ambiguity. If we detect a signal, how confident can we be that it is a genuine signature of life? I think here technosignatures comes out clearly on top. For example, if we detect a series of prime numbers sent our way down a pulsed laser beam, there's essentially no doubt that that is artificial. That's about the highest confidence we're ever going to get until they land on the White House lawn. Now, technosignatures aren't always going to be unambiguous. The example I cited before of accelerated climate change could easily be caused by some unknown natural process intrinsic to the exoplanet in question. But critically, technosignatures have the potential to be absolute slam dunk detections of alien life. Biosignatures just don't really enjoy that same high level of confidence in their interpretation. Take oxygen. Something has to be producing it for it to be hanging around in an atmosphere persistently, and on the Earth, that something is life. But recent work has shown that there are also non-biological processes which can produce oxygen. One crucial mechanism is photolysis, where ultraviolet light splits water up into hydrogen and oxygen. On the Earth, this is a minor effect, but now multiple scenarios have been identified which could ramp this up. For example, being around a highly active M-dwarf, a paucity of non-condensing gases like nitrogen, a higher initial inventory of carbon dioxide, or a higher or indeed lower initial inventory of water on the planet. All of those could work. Now, ruling these out will be a massive undertaking, and so we have to be very cautious about interpreting the detection of oxygen as evidence for life. This ambiguity problem isn't limited to oxygen either. Methane is another hypothesized biosignature. About 100 million metric tons of the stuff is produced on the Earth every year by livestock, representing a significant greenhouse gas. Like oxygen, it doesn't hang around and should be destroyed within a few centuries, even just by solar radiation. Repeated detections of methane on Mars by the Curiosity rover stoked great excitement for Martian life, but that excitement was quelled by the possibility that this could actually be just a natural geological reservoir. Martian methane is really a great example of this ambiguity problem because that is in our own backyard where we can physically visit the planet, land on the surface and scoop up samples, and yet still we are confused. When it comes to exoplanets, which of course we don't have access to their surfaces, that is going to be a far more challenging case to make this determination. So this problem might be surmountable, perhaps one day, but for now, I would take a prime number sequence over an oxygen signal any day of the week. So far, we've discussed frequency and ambiguity in weighing biosignatures against technosignatures, and my score is 1 point apiece. Now, let's get into the real meat of this video with the third argument, persistence. Traditionally, this is where biosignatures has enjoyed the most forceful argument, because proponents will point at the Earth and say, look, the Earth has had life for 4 billion years, but we've only been producing radio waves for, 100 years? 4 billion divided by 100 is 40 million, so therefore we are more likely to be looking at a planet with biosignatures only by a factor of 40 million. This admittedly seems like a pretty strong win for biosignatures, but there's actually two problems with it. The first is that number of 4 billion years, and the second is that number of 100 years. The 4 billion number isn't right, because the very earliest forms of life on Earth were largely undetectable. The easiest hallmark of our planet's biology is the oxygen produced by photosynthesis, assuming that the ambiguity issue could be resolved in principle. This oxygen, though, wasn't present until about the midpoint of life's history to date, some 2 billion years ago. This is the Great Oxidation Event, an event driven by the evolution of photosynthesis, an adaptation that was so successful that it ultimately changed the chemical constituency of our planetary atmosphere. I want to highlight that the Great Oxidation Event isn't just a blip, a temporary increase in oxygen. It represents an effective, permanent change. We can really split the Earth's history up in two, the pre-oxygen and post-oxygen eras. That oxygen was at first toxic to some forms of life, but over time, life adapted and even thrived, enabling complex multicellular organisms thanks to the enhanced metabolism possible due to oxygen respiration. Now, the biosignature proponent might say, look, so what? You've changed my number by a factor of 2, so we've gone from 4 billion years to 2 billion years. That still leaves biosignatures with a factor of 20 million advantage over technosignatures. Well, that's true if and only if we adopt that 100-year number for the technosignature lifetime. But how reasonable is that really? What we're really getting at here is the longevity of technosignatures. If we use the 100 years number, then we're really essentially assuming that our civilization will collapse tomorrow. Sure, that's possible, but it's rather extreme. Really, a better number to use here will be how long will our technological civilization last, which necessarily has to be some number at least as large as 100 years. We've done some work on this before here at the Cool Worlds Lab, so check out our video about civilization longevity to learn more. However, I think that even this kind of misses the point when it comes to the debate that we're talking about in this video, because really it doesn't actually matter how long a technological civilization lasts for. What really matters is how long do technosignatures last for. Now those are subtly different, because the former really assumes that planets just get one civilization in their whole lifetime and that's it, whereas the latter allows for the possibility of a cycle of rise and fall of civilizations over time. Let's look ahead into our future, a few hundred, perhaps even 1,000 years. Our civilization has ended. Who knows why? It could be some kind of economic or societal collapse, a pandemic that eliminates the vast majority of humans, or the collapse of modern agriculture in the face of a changing climate. But the problem with humanity is that we're incredibly pervasive, living on every landmass from remote Pacific islands to the Arctic tundra, perhaps soon even on Mars. Like cockroaches, we've infested every little nook and cranny of our planet. And so even in the face of a global collapse, it would be difficult to push us into complete extinction. Before the modern era, humans lived in small groups for hundreds of thousands of years, relying on their adaptability and intellect to live off the land in harsh conditions. Over time, humans even changed as a species, growing larger craniums, losing hair, and changing the jaw, tongue, and throat to accommodate complex language. If we go forward millions of years into the future, then our descendants may plausibly persist long after this current iteration of what we call civilization has collapsed. They would continue to evolve, and disparate populations would plausibly develop into distinct subspecies of Homo sapiens. For example, island populations might succumb to Foster's evolutionary rule and evolve smaller bodies reminiscent of hobbits. In contrast, those living in colder climates might evolve larger bodies via Bergmann's rule. Evolution is very difficult to predict, but the real point here is that not only could our descendants persist, but they may represent the branching point of an entire new subfamily of intelligent species. Indeed, it is similarly quite possible that on millions of years timescale, our evolutionary cousins in the hominid family, such as the chimpanzee and bonobo, may also eventually have descendants capable of technology. The proposition here is that if intelligence, as we recognize it within ourselves, continues to provide a survival benefit, and it is not completely eradicated from the current tree of life, then intelligence may persist until the demise of our biosphere. That's a time roughly 1 billion years in our future, when the sun's increased luminosity will eventually render the Earth inhospitable. In this picture, the evolutionary emergence of intelligence is not a temporary phenomenon, a curious blip of some kind, but rather it's a phase change for the planet. We could split Earth's history up into two, the pre-intelligence and post-intelligence eras, and mirroring the Great Oxidation event, we might call this the Great Awakening event. Interestingly, in both cases, these events are coupled to mass extinction events. In the case of the Great Oxidation event, the potent greenhouse gas methane was rapidly oxidized, which led to a global cooling of the Earth and thus a mass extinction. In the case of the Great Awakening event, well, we are living through it right now, and tragically, humans are destroying the environments for thousands of species, which is indeed leading to a new mass extinction. One might wonder, even if intelligence persists on the Earth, can technological civilizations truly re-emerge? The Industrial Revolution was fueled by oil, but our civilization has been so greedy that maybe there's not much left for future civilizations. Indeed, current estimates predict that there's only 50 to 70 years of oil left in proven reserves. On a timescale of tens of millions of years, new oil will form within the Earth just thanks to the sedimentation of organic matter, as it did previously. And yet more, the plates on the Earth are of course in continuous motion, and so over this kind of timescale, new oil reserves might just open up thanks to that motion. Of course, that point is also relevant for access to rare earth elements. Yet more on this kind of timescale, the damage that we've caused to our climate will also likely have largely recovered. So future civilizations may not have quite as much oil as we did, but likely sufficient to spark their own industrial revolution and then have a swifter transition to renewable energy sources. Ultimately, that might actually be healthier for their development, forcing them to pursue a sustainable path far sooner than we did. Now, clearly I've been speculative here, which is frankly simply unavoidable when talking about the future. But the real point of this speculation is not to claim anything specific about our planet's future, but rather merely to highlight that we should be open, just open to the possibility that intelligence and thus technosignatures might be a persistent phenomena for our planet's future. And if that is so, then 100 years as a fixed lifetime for technosignatures may be hugely lowballing it. Because if the Great Awakening hypothesis is correct, then our technosignature lifetime could be plausibly roughly 1 billion years. This would massively erode away the temporal advantage that biosignatures enjoy. It would drop it from a factors of tens of millions to just a few. And to add a little bit more punch to this counter-argument, there are actually 2 other ways that we can imagine greatly extending this technosignature lifetime. One is simply to build a kind of relic or beacon. Like the pyramids, civilizations might choose to build purposeful monuments of their existence for future generations to find. Long after the civilization is gone, these relics could persist and be detectable. This, again, allows for enormous increases in the technosignature longevity, although how long such relics could truly persist and remain detectable for is deeply unclear. A third way that we can imagine greatly extending the technosignature lifetime is perhaps the most radical option. It is the technological singularity. This is the name given to a point where artificial intelligence develops to a sufficient level that it essentially can improve itself exponentially, leading to a point of no return, a horizon beyond which predictions are opaque. This could involve a kind of post-humanity species, one blended with technology, or even simply an AI in isolation. In any case, it represents another scenario where essentially all bets are off when it comes to guesstimating the lifetime of technosignatures. Here, the Great Awakening event is not really the emergence of biological intelligence, but just intelligence more broadly. So let's come back to our scorecard of arguments in the biosignatures versus technosignatures debate. To summarize, we've scored a point for biosignatures when it comes to frequency, although we can certainly conceive of counter-arguments to that if one invokes colonization scenarios. Next, we've scored a point for technosignatures when it comes to being unambiguous. It's not always going to be unambiguous, but it certainly has the potential to be so. And last but not least, we have persistence. Based on the Earth, biosignatures have persisted for 2 billion years and should probably last for another billion, giving 3 billion years in total. Technosignatures, on the other hand, have only been present for a century or so, but crucially, as we've argued here, once it emerges, it might be very difficult to expunge intelligence on a planet. In many ways, the Earth is now infested with intelligence, and complete eradication may be very difficult barring the most extreme mass extinction events. With 1 billion years of open road ahead of us, technosignatures in some form or another may plausibly persist for cosmic timescales. This would smooth out the temporal advantage of biosignatures to a modest 3-to-1. Combined with the more speculative nature of this extended technosignature scenario, I think it's fair to score this as a point for biosignatures, but crucially, I don't think we can call this a dominant victory, more like a modest preference. In total, the scorecard suggests that yes, biosignatures are likely the best approach, but if we are investing $10 billion in a biosignature search, then the scorecard also suggests that it might be worthwhile to invest a fraction of that money into a technosignature search as well, perhaps a paltry $1 billion, the kind of money that Jeff Bezos might call loose change. Fortunately, astronomers are now coming around to the idea of a technosignature mission, with multiple ideas being discussed in the community, such as a far-side lunar radio telescope, a terrascope atmospheric lensing concept, or a waste heat survey satellite. So what do you think? Should we build a flagship technosignature mission one day, or do you think it's best to bet on biosignatures alone? And do you think that intelligence could persist, or will humanity ultimately represent an anomaly in the evolutionary record? Let me know down below. This is very much an open dialogue type video, so I really do want to hear your thoughts about this subject. Perhaps in 100 million years from now, a future Earthling might look back at human civilization and wonder, what were we like? Did humans ever look up to the stars? Our time here might be finite. Everything eventually ends, but I'll be damned if we don't try to figure out our place in it all before our time comes. So, until the next video, stay thoughtful and stay curious. Thank you so much for watching, everybody. I hope you enjoyed this. The ideas and concepts presented in this video are based on real research happening at the Cool Worlds Lab at Columbia University. In fact, I want to thank the latest donors to the Cool Worlds Lab, that is Jacob Black and Reza Ramazan-Khani. Thank you so much for your support. If you too want to help us out, then be sure to click the link up above where you too can become a Cool World and get access to special perks. So until next time, see you around the galaxy.